Right, in this screencast we're going to look at a branch of mathematics known as kinematics, which refers to the calculations of the movement or the motion of a point or a particle in a straight line. Sounds pretty dry, and it probably is, but it's an application of rates of change, which is what we've been looking at the last few days. So what I need you to do perhaps is just to start it off by getting a little heading down here: displacement, velocity and acceleration. These are some terms and some concepts we're going to explore, and so we'll start off by just defining what each of these things mean, and that'll get us started. But the displacement, velocity and acceleration I'm sure you're familiar with, but we just need to be careful about our definitions and make sure we understand them. So, but displacement might be a slightly strange. Okay, continuing. So the displacement is the particle's position on the line. So if you just imagine it's like a number line, and there's a particle that's just sort of bumping along it. You know, it's going this way, it's going this way. It's just the displacement is where it is, and displacement just means is literally the displacement from the origin. So if the origin is here, say that's the point 0, and if the point's there, then it's to the right of the origin, so it's positive. But if it moves and turns up down here somewhere, then it might be at -1. So the displacement is just where the particle is. Now, the velocity is the rate of change of the particle's displacement with respect to time. Now, that makes sense. We understand that as a particle moves, you know, backwards and forwards, we can calculate its velocity. Now, velocity is different to speed. Speed is not directional, and that is speed is not concerned with direction. It's just how fast. Velocity is concerned with direction. So if a particle is going this way, then it has negative velocity. If it's going this way, it has positive velocity. And the acceleration is again directional, and it is concerned with the rate of change of the particle's velocity with respect to time. So how it changes in velocity. If you're going at a constant speed, then there is zero acceleration, and if you're slowing down, then it's negative acceleration, etc., or deceleration. It means the same thing. Okay, so there's some terms as we move into just looking at an example now. The displacement of a particle, and this is fairly typical. We're given an equation here which gives us the displacement of the particle, and what we can do is we can calculate where the particle is at any time t by substituting value in for t. The function for describing velocity is right there. Okay, so what we there's nothing specific I want to do with this, just have a look at how this works in practice. So we might just want to go, okay, well, where is it initially? So let's just get a little story. The story of the particle. I can just sort of build this up a bit. So initially at t equal to 0, the particle is at the calculation is S0, which equals 0. So it starts off at 0. So if we're going to have a little look at what's going on here, if we just look at the line and where the point is, time equals 0, it's there. Alright, that's t equals 0. Alright, now let's find out, well, where is it after a second? So at S1, what's it equal to? So after 1 second, t is in seconds. We're going to say t is in seconds. I believe that's the case. So we've got, after 1 second, we put s equals 1 in here to the displacement function, and we get 1 minus 6 times 1. So we get 1 minus 6, which is equal to minus 5. So that tells us that we initially, when t equals 1, we're back here at minus 5. Okay, and then at t equals 2, we could find another spot, and we could build up a little picture this way. S2 is 8 minus 6 times 4, 24. So 8 minus 24, which is equals minus 16. So it keeps heading off in this direction. When at t equals 2, it's now shoved right down here somewhere at minus 16 after 2 seconds. So the particle is just buzzing off in this direction. Now we could find out its velocity. So we could say, all right, well, let's now calculate its average velocity in first 2 seconds. That's going to equal, that's just going to equal its change in displacement, which is 0 to minus 16. So it goes 16 to the left over the time elapsed in the first 2 seconds is 2. So it's minus 8 meters per second. Just assuming that we're talking in meters for our displacement and in seconds for our time. So there's some news. Okay, but we can find out the velocity after 2 seconds, instantaneous velocity, because we've got a instantaneous velocity after 2 seconds is equal to v2. This one here, so that'll be v2. So we put in 2 into the v equation. 3 times 2 squared, that's 3 times 4 is 12, minus 12 times 2, so 12 minus 24, which is equal to minus 12 meters per second. So after 2 seconds, it's going at minus 12 meters per second. It's still heading off in that direction to the left. So we're right now to proceed with the work requirements from exercise 18E, starting at page 525. That will be our task for Tuesday in class. Let's remember that we need to get those work requirements done in class. So come to class ready to get stuck in. I'll see you then.